All right, greetings, welcome back. Part 2 of Section 7, Chapter 8, L'Hopital's Rule for Indeterminate Forms. Okay, so my calc babies, we need to practice this new way of evaluating limits. And as I mentioned in the previous episode, part A of this section, L'Hopital's rule is set up beautifully for when your limits take the indeterminate form takes the form of 0 over 0. As long as we define the numerator to be some function f, the denominator to be some function g, as long as those guys are differentiable on an open interval, and they contain c, which is the limit you're trying to approach. Now, that doesn't mean that c actually has to be defined, right? But is assuming that f and g are differentiable, and of course assuming that when you're not dividing by 0 when you take your derivative of g, then this method works perfectly. It also works for forms of infinity over infinity, negative infinity over infinity, and so forth, provided the limit on the right exists, right? Exists, I believe, exists or infinite. So that's kind of our disclaimers, right? Some conditions that we wanted to get out of the way, and let's go ahead and jump right in. So I'm going to go ahead and take, I think what I'm going to do is grab this picture, right? I'm going to try to park that guy. Actually, I'm going to go ahead and get rid of it. Give myself some space. Okay, so the way I'm going to do this is I'm going to rewrite the limit down here as x approaches 0. But I'm always going to go ahead and take my derivatives up here. All right, so this is going to be f prime. This is going to be g prime. And then I'm going to kind of drag and drop and then continue with the approach, right? So if I take the derivative with respect to x of that numerator, so what are we going to get? Well, the derivative of -1 is going to 0 out, and that's just chain rule to take the derivative of e to the 2x. That should give us 2e to the 2x, right? You know that. Just let u equal 2x, f prime of u times u prime. And then the derivative of x with respect to x is just 1. So what we end up getting in this case, let's go ahead and get rid of this guy. So what we end up getting is just 2, the limit as x approaches 0 of 2e to the 2x. All right, and now we're going to jump in and substitute our 0. So that ends up being 2e to the power of 0, right? Which is just simply equal to 2 times 1, which is equal to 2. So not bad, right? Fairly easy. Let's continue here. Continue in our game. So now we want to evaluate the limit as x approaches infinity of ln of x over x. Again, you can always start with trying your algebraic techniques, but I'm going to go ahead and come down here, write my limit as x approaches infinity, and I'm going to go ahead and take my derivatives right now. So in this case, we have f prime equals g prime equals, so the derivative of ln x is just 1 over x. The derivative of x is just 1. So 1 over x divided by 1 is just 1 over x. And now let's bring that guy down here. And so, well, you recall this, right? So the idea is the limit as x approaches infinity of 1 over x, the rule was anytime you're trying to take a constant and divide it up an infinite amount of ways, you're going to get nothing. Right? That was I mentioned that in the previous video. If you got $1 and you divide it up an infinite amount of ways, well, that's very generous of you, but of course no one's going to get anything. So let's continue. So we got the limit. In this case, it's the limit as x approaches negative infinity. So what you're going to see, I believe, in this case is we're going to end up having to use L'Hopital's rule more than one time throughout the same problem. I'm going by memory, so I can't. So I could be wrong about that, but just looking at the structure of it, I think this is going to be one where you're going to have to apply it multiple times. So ready? Let's go ahead and get started. So we start with taking the derivative of the numerator, f prime, and then we take the derivative of the denominator. So let's go ahead and do that. So the derivative of the numerator is just 2x, and the derivative of the denominator, remember that's just u substitution. You would let u equal negative x, then it's f prime of u times u prime. That gives us negative e to the negative x. Right, so now, at that stage of the game, we're here. So stop, bear with me. Now, if we would have used direct substitution, we would have got negative infinity over, or something like either positive infinity over or positive infinity, or something like that, or negative infinity. If we were to apply the evaluate the limit right now, we would still end up with infinities over infinities, right? Negative infinity over negative infinity. I want to make sure I didn't say that too quickly. Right now, if you were to evaluate the limit at the very beginning, you would get infinity over infinity. Okay, so indeterminate. So we use L'Hopital's rule. Now, if you were to evaluate the limit right now, you would get negative infinity over negative infinity. It's still undetermined as to whether the limit actually exists. Right? So, well, what do? We use L'Hopital's rule again. So let's go ahead. We're going to take the derivative of the numerator. We're going to take the derivative of the denominator. So this time the derivative of the numerator is just 2. And the derivative of the denominator, this is going to be, u would be negative x, and then multiply that by that negative. So it's going to be, well, it's going to be positive e to the negative x. So you're not done, right? I mean, a limit should be a value L, that you are approaching as x approaches another value. So at this stage, you actually evaluate the limit. And in this case, again, you can think about substituting, if you will, whatever it means to substitute an infinity into an expression. So negative infinity, so this would end up being e to the negative infinity, all right, or 2e to the power of infinity. Well, it's again very nice of you. That's just 2 to the infinity. So now you have $2, and you have decided to divide it up by an infinite amount of people, but yet still no one gets anything, right? So continuing. So now let's, at least I think now we're going to run into some scenarios where we start to see some of those other indeterminate forms. Ready? I'm going to kind of scroll back just a little bit. This is from a previous video. So we're now going to start to see some of these other indeterminate forms. 0 times infinity, 1 to the infinity, 0 to the 0, things like this. But the goal, notice the goal is going to be, can we rewrite it in a 0 over 0 or infinity over infinity form? Because if we can, then we can just go ahead and apply L'Hopital's rule. Okay? So let's go ahead and take a look at our limit. Now, in this case, notice, and this is very important, notice you don't have a quotient, right? You don't have an f prime or an f over g. Well, let's rewrite this. All right, so let's notice that we can rewrite, let's think about it. So negative, oh no, that's e to the negative x multiplied by the square root of x. Are you with me? Maybe you're already thinking about this. You can rewrite that as the square root of x over e to the positive x, right? So we have this negative exponent that's going to allow us structurally, where it's going to allow us just to move to the denominator. So now the problem is the limit as x approaches infinity of the square root of x over e to the x. And this is actually what we wanted, okay? Because we started off, it was written as a product, now it's written as a quotient. And remember, L'Hopital's rule is all about the derivative of the numerator divided by the derivative of the denominator, the quotient of those, and then finding the limit, right? So we needed to rewrite it as a quotient before we could continue. And now let's just go ahead and I'm going to write the limit down here, and I'll take my derivatives in just a second. Okay, so let's go ahead and take some derivatives. So f prime, g prime. All right, well, the derivative of e to the x is just e to the x. And the derivative of the square root of 2, I hope that makes sense, that the square root of, square root of x can just simply be written as x to the power of 1/2, right? Because this symbol just means something to the power of a half, all right? It's a fancy way of writing a fractional exponent, 1/2. So taking the derivative, this would be 1/2 x to the negative 1/2, right? So taking my derivative, this would be 1/2 x to the negative 1/2, which we can rewrite as 1 over 2 square roots of x, right? So that's 1 over 2 x to the positive 1/2, and we'll go back and rewrite it as the square root, using the square root symbol. All right, so now let's go ahead and write down here what we want to be able to take the limit of. So we have 1 over 2 square roots of x over e to the x. All right, and let's think about, because this is a complex fraction, so we have a fraction divided by e to the x, and we want, we're going to want to rewrite this. So let me rewrite. So all I'm going to do, just let me come down off to the side here. All I'm going to do is we have 1 over 2 square roots of x divided by e to the x, right? We can think about that as e to the x over 1. We flip, we multiply, and now that allows me to rewrite this as 1 over, so 2 square roots of x e to the x. Okay, so notice it's just some preliminaries, right? Some little bit of algebraic manipulation to get it into a form where we can now use L'Hopital's rule, right? So at this stage, if you evaluate the limit, we end up with 1 over, well, 2 times the square root of infinity times e to the infinity is just infinity, which, boom, 0. Okay, so maybe it's worth taking a second here. So this might be an epic failure, but I'm gonna go into Desmos. Let's see if I can make this go smoothly. And let's recall that the original problem was e to the power of negative x, right, times, let's see here, where is the square root is here, times the square root of x. All right, now, let's see if I can zoom in a little bit here. So why am I taking a break? And no, look at this. Watch. You ready? Are you ready? Because I'm about to use some awesome